So good morning, everyone. We will be starting today our MOOC operating system lecture 2 of module 1. So in this lecture, we will be understanding what do we mean by the process and its various concepts. So first of all, let us understand what do we mean by what is the difference between a program and a process. So program is a passive entity. Whatever code we write in any of the language, that code has got no capability of taking the or utilizing the computer resources, because whatever we want, whatever the code has been written, it is normally saved into the hard disk. So it has got no power of its own, and that is why it is known as passive entity. When we run that program and it is uploaded into the RAM, or that is random access memory, then we say that it now has become an active entity, because now it can utilize all the computer resources. So it becomes a process. So program is a passive entity and the process is a active entity. Now, whenever a program is executed, then it becomes a process, and then that process has got different states. So basically it has got 5 different states, namely the new, ready, running state, waiting state, and the terminated state. So whenever a new program is executed, then it is automatically come into the new state. So that new state is basically present into our hard disk, where all the newly executed process are stored. Now, when they are admitted, so depending on the size of the program or size of the process and the size of the available memory with our RAM, the new process is got admitted. Now, there may be more than one process which are waiting in the new state to get admitted into the RAM. So the scheduler which chooses the process from the new state and bring it into the ready state is known as long-term scheduler. As the name suggests, long-term scheduler, it is invoked after a long time. What do we mean by long time? It simply means that whenever any existing process is terminated or finished its execution, then it is taken out of the RAM. So that space is now become empty. So the space which is now empty can be filled by some another process, and then the long-term scheduler is invoked to bring in a new process from the new state into the ready state. So whenever a new process is admitted into the RAM, then first of all, it had to go into the ready state. Okay. Now, on which criteria the long-term scheduler chooses the process from the new state and bring it into the ready state? Basically, first and the foremost thing is the size, of course, because whatever size is available in our RAM, that the program size should be that only, not more than that. So the first criteria to choose a process from the new state and bring it into the ready state is the size of the program or size of the process. And the second thing which is taken into consideration by the long-term scheduler is that at every time we want that there should be a good mix of both CPU bound as well as input output bound processes inside our RAM. Now, first of all, let us understand what is CPU bound and what is input output bound process. So whenever we make any program, then it is nothing but a combination of statements which needs either the CPU for calculation or computation purpose, or the input output device, like the keyboard for taking the input, or the printer for giving the output, or maybe storing something into the hard disk. Again, it's a input output command. So whatever commands we are writing, they can be classified into 2 basic categories. One is the CPU which requires calculation, and another is the input output devices. May it be the keyboard, it may be the hard disk, it may be the printer, or so on. So now the process which are having more statements which are computation related, that is more of a CPU is required, then we say that this particular process is a CPU bound process. It means what? That if the number of statements which requires calculation are more than 60 or 65% in our complete program, then we say that that particular program or process is a CPU bound process. And if the number of statements are, let us say, if we have got 100 statements and more than 60 or 65 statements are related to input output commands, that is either they are requiring the input from the keyboard or they are giving certain output, then we say that if 65% of the statements are requiring the input output devices, then that particular process we can call a input output bound process. So now what our aim is that both the CPU as well as the input output devices should be utilized at its maximum limit per unit time interval. So what we want for that, there should be, if I've got 10 programs or 10 processes inside the RAM running at some particular time interval, then what we will be expecting is that 5 processes should be CPU bound and 5 processes should be input output bound, so that the CPU as well as the input output devices are continuously being utilized and the overall efficiency of our system is increased. So the second criteria, as I have mentioned, for the long-term scheduler to bring the new process from the new state into the ready state is it should bring that process so that it will maintain a good mix of CPU bound and IO bound processes inside the RAM. That is, let us say I have got currently 10 processes running in my RAM. Now 5 are CPU bound and 5 are IO bound processes. Let us say one IO bound process is finished. So now we are left with 9 processes inside the RAM, and one process we can bring in. So the process which is terminated is IO bound process. So now the long-term scheduler will look for the IO bound process inside the new state, which has got either the same size or the size should be smaller than whatever space which is available in the RAM. So it will try to bring in the IO bound process so that a good mix of CPU bound and IO bound process can be maintained inside the RAM at that particular time. So these are the two criteria on the basis of which the long-term scheduler will be bringing the processes from the new state into the ready state. Now, once the process has came into the ready state, then it can be allotted the CPU. So if I've got a single processor system, then only one process can be in the running state at any particular time. So let us say I've got 10 processes in total in our ready state. Then the CPU will be choosing one process out of that 10 processes to bring it into the running state. Now, the criteria on the basis of which the CPU chooses a process from the ready state and bring it into the running state will be based on the CPU scheduling algorithms, which we will be studying in our upcoming lectures. So, as you can see here, from the ready state to the running state, the scheduler will be dispatching the process, or the CPU will be scheduled to one particular process inside the ready state. So only one process can be in the running state at any given time interval. Okay. Now, once the process is completed its execution, then the process can go from running state into the terminated state. That is, it will exit from the RAM. Now, from the running state, the process can go either into the waiting state or it can go back into the ready state. So depending on the kind of scenario, the processes will be going from the running to the either to the waiting state, and after waiting, then again they will be going into the back into the ready state, or the processes can be going from the running state directly to the ready state. So as we can see here, the process which are going directly from running to ready state, and we have written interrupt there. So now let us understand what do we mean by interrupt. So there are basically two types of interrupts, software interrupt and the hardware interrupt. And these are high priority processes which needs immediate attention. And if the immediate attention is not given to those priority processes, then that process might crash. For example, let us say I'm talking to two students at some particular time. Now, a third student come to me and say, excuse me, sir, I've got some urgent work. So can you please listen to me? So what I will do, I will simply interrupt those two students which I am already talking to, and I say to the third student, okay, tell me what happened, what is the urgency, right? Similarly, in our computer system, there might be many scenarios when the high priority process needs attention immediately. For example, suppose I am printing a file. So there will be, let us assume that I've got 1,000 pages in my file which needs to be printed. Now what happens? The CPU is a pure electronic device. So its speed is very, very fast. But the printer is the electromechanical device because it will have to rotate the papers also. So it obviously requires the mechanical motors also. So its speed is very, very slow as compared to the CPU. Now what happens is to match up that speed, a printer is being provided by one buffer. So buffer is a very fast memory which can communicate with the CPU in a very fast manner. But that buffer is a kind of high-speed memory, but it cannot be unlimited because it might be the case that I want to print 1,000 pages. It might also be the case that I want to print only 5 pages. So I cannot keep my buffer size unlimited. So we fix the size of the buffer of the printer. So let us say we have fixed the size of the buffer of the printer to, let us say, 10 pages. So what happens, since I am printing the file which is 100 pages long, so what CPU will be doing, CPU will be taking the first 10 pages from the 1,000 pages of my file, then it will simply store them into the buffer. Since the buffer of the printer is also a very high speed memory and can communicate with the CPU at the same speed, so the 10 pages will be kept into the buffer, and then the printer will slowly start taking one by one pages from the buffer of the printer, and it will start printing them. Once all the 10 pages are printed, then the printer will send the hardware interrupt to the CPU that I am finished with the 10 pages, fetch me next 10 pages. So this interruption by the printer to the CPU will be hardware interrupt generated by some hardware device. So it is a high priority process, or it is a high priority service. So whatever CPU will be doing at that particular time, it will simply stop that, and then first of all fetch the 10 pages to the printer, and then again go back to whatever previous work it was doing earlier. So this is what we mean by interrupt. So from the running to ready state, it can, if some high priority interrupt is generated by any of the hardware device, then the process which is currently running will be simply sent back into the ready state. The CPU will be fetching that particular interrupt, and then again resuming with that same process which it was previously dealing with. So in this case, the process might go from running to ready state directly. Also, there might be the case that we have allotted, let us say, some particular time interval or time slices to every process which are in the ready queue, which is a most common scenario when we are dealing with multiple users, like in Google search engine. So what do you think, that in Google search engine only one user is searching something at one time? No, it is not the case. So many users might be searching at the same time. So what happens, that Google will be switching the CPU of that server to every user in a very fast manner. And since the CPU is a pure electronic device, so only a small fraction of time, if the CPU gives to me, and then uh, uh, it is again switched to another user, and when it comes back to me, then I will always feel like that the CPU is always with me. I have already discussed the same example in my previous lecture. Let us again just revise that example. What happens? Suppose I've got a 1 gigahertz processor. So what happens? What do we mean by 1 gigahertz processor? It means 10 to the power 9 10 to the power 9 cycles can be generated by that CPU in 1 second. And normally any command requires 5 to 10 cycles for its execution. Let us say if I've written C equal to A plus B, then it might require 10 to 12 cycles. So if a CPU has got 10 to the power 9 cycles generated in 1 second, then you can think of that my command is requiring only 10 cycles out of that 10 to the power 9 cycles. So what the CPU will be doing? So within if the CPU is given to me even for a fraction of a second, then also it can execute thousands of my commands in that fraction of a second, and then the CPU will be switching back to the another user. So suppose the CPU is allotted, let us say 1000 users are there, and the CPU is giving 1 millisecond to every user. So then what will happen? It means 1 by 1000th of a second, the CPU is with me, and then it will be switching to the another user, and then again it will be switching to the third user, and so on. So for traveling or for giving the time to every of the 1000 user, the CPU will be back again with me after 1 second. Yes. So because I am giving the CPU time to every user for 1 millisecond, that is 1 by 1000 of a second, and that is sufficient for me to execute several of my commands. So that is how the CPU is utilized, right? So in that case also, this kind of scenario is known as time sharing, time slice. So a small time slice is given to every user by the CPU, and so when the time slice is expired, like by 1 millisecond is completed, then the CPU will be leaving my process or that particular user and switching to another user. So in that case also, the process will be coming back from the running state to the ready state. So in that case also, it will be directly coming here. Time slice expired. Okay. So in these two scenarios, the process can come back from running to ready state, and from running to waiting state, the process will be normally going whenever any kind of input output event occurs. So we will be discussing those scenarios when the process will be going from running to waiting state, and after that input output event is completed, then again the process will be switching back from waiting to the ready state for the next command to be executed by the CPU. So this is how the process keeps on switching from one state to another state. Okay. So as I've already told you that any process is nothing but a combination of either the CPU related statements or input output related statements. So let us say I've got one process P1 and I've got 5 statements of CPU. Then after that CPU, obviously some input output statements will be there. So let us say 10, 20 statements are there or input output statements. After IO statement, again, there will be CPU statements and so on. So alternate fashion, we have got the CPU and input output statements in any of the process, in whatever language we build those programs. Okay. So let us say, so these 5 statements of CPU related requires some fraction of a time. Okay, so though that particular fraction of a time I will call CPU burst. It means CPU will be giving that much time to execute all these 5 statements or 10 statements which are in a sequence. Again, the IO burst come, then the CPU burst come, and the IO burst come, and so on. So in any process, always the first kind of burst will be CPU burst, and the last burst will also be a CPU burst, and in between there will be an alternate fashion. We have got CPU burst and the IO burst in alternate fashion. Okay, so thank you.